Completing the square, solving quadratic equations.
This is the second video of recording examples, as well as I'm going to show you something else that completing the square has done for us along the way.
Our third example is negative 2x squared minus 3x minus 5 is equal to 0. If you would like, pause the video, see if you can solve this one on your own using the completing the square method, and the answers are listed to the right underneath that orange box. Okay, step number 1 says we need to divide everything by a to make our leading coefficient 1. Our a term here is a negative 2, so I need to divide both sides of my equation by a negative 2. On my right-hand side, 0 divided by any number simplifies to 0. On my left-hand side, what I'm going to do is divide each term by 2. So first, I have negative 2x squared divided by negative 2, and those negative 2 cancels out, leaves me with x squared. Next, I have negative 3x divided by negative 2. Negative 3 over negative 2 makes it a positive 3 halves x. And last, I have negative 5 divided by my negative 2. Again, my negatives cancel out, making this positive, and then that simplifies to just 5 halves. So I have finished step number 1. Step number 2 is I need to move my constant term to the other side, isolating my two variable terms. So I do that by subtracting 5 halves from both sides of this equation. That leaves me with x squared plus 3 halves x on the left and a negative 5 halves on the right. And that finishes step number 2. Step number 3, I need to put in my blanks, both at the end of each side of my equation. And then I need to fill in these blanks. I need to fill them in with 1 half b squared, where my b term is the number in front of the x, the single x. So my b in this example is 3 halves. So I'm going to fill in my blanks with 1 half times my b term, which is 3 halves, and then squared. Multiply your fractions straight across. 1 times 3 gives me 3, and 2 times 2 gives me 4. Once I square that, or square each piece, on the top, 3 squared gives me 9. On the bottom, 4 squared gives me 16. So that's what I'm going to be filling in my blanks with, is 9 over 16. And whenever I put in one of the blanks, I'm going to put the exact same thing in the other blank. So basically those end up balancing or canceling each other out. Just rewriting my equation at this point, I have x squared plus 3 halves x plus 9 over 16 on the left, and that is equal to negative 5 halves plus 9 over 16 on the right. So I've done the first part of my complete the square process. Now I need to factor the trinomial on the left. So setting up my parentheses because I do not have any common factors. Factors that give me x squared to go in my first places come from x times x. Factors for my 9 over 16 to go in my last places. Remember, those are always going to be the same thing here before you square it. So that's going to be a 3 over 4 and a 3 over 4. Because when you multiply those, that gives you 9 over 16. And when you add those, that gives you 3 halves. Whatever your sign is here will be the same sign in both of your parentheses. So in this example, it's addition. Now, that factors as a quantity squared, hence the complete the square process. On my right-hand side, I need to add these fractions. I'm going to do it by finding a common denominator. And my least common denominator between 2 and 16 is, of course, 16. I put them both into that form by multiplying my first one by 8 over 8. That gives me negative 40 over 16 plus a 9 over 16, and negative 40 plus 9 gives me a negative 31 over 16. Now I have my complete the square process set up. So now I have finished step number 3, and I need to isolate my variable by using my square root property. It says to get rid of this square here, we're going to force in a square root. And whenever you force in a square root, you will also force in a plus or minus. On the left, my square and my square root cancels out, leaving me with x plus 3/4. On the right, I have both positive and negative, simplifying what I can. On the top, I have square root of negative 31. Now, the square root of 31 doesn't simplify, but I can take the square root of the negative to give me an I. On the bottom, square root of 16 does simplify, and that gives me a 4. To finish my process by isolating my x, I subtract 3/4 from both sides. And that gives me the answer of x equals negative 3/4 plus or minus the square root of 31 over 4, and then I'm just moving that I from the top of the fraction to the middle of the fraction. And that gives me my final answer. X equals negative 3/4 plus or minus root 31 over 4 times I. If the problem asks for the solution set, it's the same exact answers except for you put your answers in braces. So here is the last example in our completing the square process. Okay, I have told you that I will probably never use the completing the square process to solve a quadratic equation, just because I have 3 other processes that I like better. However, if you like the complete the square process better than the factoring method or the quadratic formula method, you are more than welcome to use this process as well. Now, even though I will never use the completing the square process, it is actually very useful for me in a roundabout way. And that roundabout way is to answer the question of where did the quadratic formula come from? So when we were solving equations by using the quadratic formula, I just gave you that formula and I did not tell you where it came from or how it was invented. The way it was invented was by completing the square. So I'm just going to take this quadratic equation put in standard form here of ax squared plus bx plus c, and I'm going to complete the square with it, and that's going to show you how the quadratic formula was invented. So my steps. The first step is to get rid of my leading coefficient a by dividing everything by it. So on the left, my ax squared over a cancels out to give me x squared. I have bx over a, or just b over ax, plus my c over a. On my right, 0 divided by a gives me 0. So there I have finished my first step by making my leading coefficient 1. My second step was to isolate my 2 variable terms by moving my constant term to the other side. So I'm going to subtract the c over a from both sides. On the left, I have x squared plus b over ax. On the right, I have negative c over a. Now I need to put in my blanks. And to fill in those blanks, it goes 1/2 times my b term squared. My b term in this point is b over a. So I'm going to fill in my blanks with 1/2 times b over a squared. Multiplying my fraction straight across, 1 times b gives me b, and 2 times a gives me 2a. Then when I square it, I get b squared on the top, and on the bottom I'm going to square all my pieces, so 2 squared gives me 4, and a squared gives me a squared. So that's what I fill in both of my blanks with. So at this point, I have x squared plus b over ax plus b squared over 4a squared. On the right, negative c over a plus b squared over 4a squared. On the left, I need to factor this, and on the right, I need to simplify by combining those fractions. Let me focus on the left first. I have x times x to give me my x squared here. Then to come up with my last pieces, that is going to come from this here, but remember, it's always what we see before we square it. So my green places fill in with b over 2a. And that's because it multiplies to give me my last, b squared over 4a squared, and it adds to give me my middle. My outside is b over 2ax plus my inside b over 2ax. Combining my top gives me a 2b over my bottom 2ax, cancels out my 2's, and leaves me with this b over ax that I have here. Whatever my sign is here will be my sign there, so this is all positive. And that factors as x plus b over 2a quantity squared. On the right, I need to combine these fractions by giving myself a common denominator. I do have one a in common, which is wonderful, but then I also need to fill in my other missing pieces, and this one has a 4 and a second a. So I'm going to multiply my first fraction by 4a over 4a. That leaves me with a negative 4ac over 4a squared plus just my second fraction, exact same, of b squared over 4a squared. So in the top, I have negative 4ac plus b squared over my common denominator of 4a squared. Now if you look a little bit closer here, you start to see some things that resemble the quadratic formula. On my right-hand side, I'm just going to rearrange some things. We usually don't like the negatives in front, so I'm going to put my b squared first and then minus my 4ac last. And that's still over 4a squared. And just copying down my left-hand side. Now you should definitely see some things that resemble the quadratic formula. To finish my complete the square process, I have a squared here, and to get rid of that, I'm going to force in a square root to both sides. And if I force in a square root, I also need that plus or minus. On the left, I have x plus b over 2a. And on the right, I have positive and negative. I'm splitting those square roots up. On the top, I'm going to leave it as is, b squared minus 4ac. On the bottom, I can take the square root of 4a squared. The square root of 4 gives you 2, and the square root of a squared gives you a. Now all I have to do at this point is move this b over 2a to the other side to get my x isolated. And I do that by subtracting b over 2a from both sides. So I have x equals negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. Now, I pretty much have the quadratic formula at this point. All I have to do is just combine these fractions, and since they have a common denominator, that makes it real easy to do. I have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that is my quadratic formula. So you can see that even though I most likely will not use a completing the square method to solve my equations, it's still useful to know how it works because that is how our quadratic formula was invented. And at this point, you should be able to solve any equations using the completing the square process. If you don't want to, that's fine. Again, you have 3 other methods to help you solve quadratic equations. But the reason that I went over this method with you is so you can use it when we graph quadratic equations and if you ever need it in a trig class.